Hello, my name is Ugo, and this is the unique paths problem. So we were given the inputs of two integer numbers called m and n, um, and they represent the 2D grid basically. So we have a grid of numbers, m represents the rows, n represents the columns. And our goal or output or desired output is an integer number representing the total number of unique paths that the robot can take from the starting position of 0, 0 down to the finished position that will always be at m minus 1, n minus 1. Yeah. So this one, a unique path essentially just means that, you have at least one difference between a path between two different paths. So, if you have one that goes down, down all the way to the right, the one difference would be one down to the right once and then down after that, I guess. I mean, that would be two, but you get the idea. The specific movements that the robot can take are very limited, which makes it a little easier. The robot can only move down or right at any point in time, so you can't have the robot go down and then to the right and then up again and then left or something like that, because then that would be infinite possibilities. This makes it a lot more restricted and something that we can actually calculate. So if we can go down, right, right, down, down, right, or down, down, down. But we can't go back or up. So, uh, yeah, it eliminates a lot of options as we step through. And we're just supposed to find the total number of unique paths. So I was watching a video. I think I could probably find it. I might have closed it. No, I closed it. No, I was basically looking at for DP problems because this is one of them. Dynamic programming. Pretty sure it says it down here too. Yeah. I didn't look at this beforehand, but yeah, it's dynamic programming. I had seen it before in NeetCode as a dynamic programming problem. I hadn't done it before, so I wanted to just look up like, hey, how do you like problem solve these type of things? Because like there's two pointers and stuff like that, where you have a conceptual idea of how to approach it, uh, some general algorithms that you can take and use in those cases. So like in two pointers, it'd be fast and slow. It would be converging. It would be converging and I guess the sliding window. So yeah, like there's like approaches, right? And the thought process helps you basically have a general like thought process when looking at these types of problems. So being able to identify these problems in the first place just by reading them, and then also knowing like, okay, let me look at the question for specific like hints that could possibly tell us, okay, this is the thing that we need to do. And one of the things that I saw repeated across the two videos that I saw for explaining DP was basically cut down the problem into smaller problems. So just make sub problems of the problem. And so that's kind of what I thought of originally, and that's why I went originally with a DFS, or well, this would be DFT solution, a depth first traversal solution, where we basically will start, or not really start, but we'll traverse to the end, and the end will be our base case, basically. So we have a base case of m minus 1, n minus 1, because that is the end, and we're going to make that 1. And then we're just going to make everything look at the value below it and the value to the right of it, because those are the only two directions that it can go. So if you go like to the right here, all possible paths that you can take will be below it or to the right of it. So then it's like, okay, if I step here, the total number of unique paths that I can take will be the total number of unique paths here and the total number of unique paths here. And the total number of unique paths here is the same one as here, and then here and here. But here we're out of bounds. So I made a condition that if we're out of bounds or at m or n, we will return 0 because there are no unique paths outside of the bounds that we were given. So yeah, the original solution was simple, just a simple boundary checker and then a final or a base case solution to start returning from. This one occurred more often because we're always going to check down, 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 or right, 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 right. But there's only one time that this is going to occur, so I put this above it, just a little efficiency boost, but it's not really anything that's going to be drastic. And yeah, that was the original two base cases. We checked the downward value by increasing the value of y, so we go down 1, but keeping the same x value. We keep going down all the way until we reach an out of bounds position where we would return 0. And once we get here, that means we have a down value, then we go to the right value, and then we do DFS to the right. So we would just go all the way to or we would just go right and then down, right, down, right, down, right, down, right, down, right, down. Or, well, not right here. Once we go right here, we'll see that it is the case here. It's going to be the base case. And that's when we return 1. The 1 gets returned right here. The 1 right here will be stored in the right value. Down value had 0 because of that. So we just return 1, and we get a bunch of 1s in this first row. And then from there, we've checked right, and we checked down from this position, so we go back up. And then the total here is going to be this plus whatever is here, so then we just do the same thing over here. Now, the problem is that this is inefficient, or this original approach was inefficient, because once we start going over here and go back down, we've already calculated this, the total number of unique paths right here. So why do we have to do it again? And I didn't notice that originally, so my first solution was just this. This is pretty simple. We just returned the right and the downward value at the end after doing the DFS and then downwards and to the right. It was pretty simple, from 0, 0 all the way down to n minus 1, n minus 1. But the problem with this was time complexity. It was constantly going down all the way to the right, down all the way to the right, down all the way to the right, and then do that for basically every step. So it was very bad, very inefficient. This isn't really much more inefficient, or much more efficient, but it helps a lot, I think. Well, okay, this one's inefficient, is very inefficient, but it's a lot more efficient than the previous solution because I use memoization. So I've always heard of this ever since I did Fibonacci number or Fibonacci sequence, whatever the LeetCode problem is. I did the original one, and I was like, okay, well, there's not really any way I can improve this, is there? And I submitted it. It got one of the worst scores possible. So I looked it up. I saw that memoization was one of the possible. I lost train of thought. My brother walked in. What was I saying? I'm not sure what I was saying. I think I was talking about memoization. I'll take it back there. Yeah, Fibonacci sequence, right. I was talking about that. The Fibonacci sequence problem, it was very inefficient. The method I used was inefficient, and I searched up how to do it more efficiently, and people were saying different alternative methods. One was called memoization, but that used a hash map, and I didn't know how to use hash map back then. I didn't have any data structure knowledge at all. I basically only knew arrays and recursion. As far as I went, I didn't know what an object was. So yeah, I lacked a lot of the skills. I needed to solve that type of problem like that. So I decided finally to try learning what memoization was. I searched it up, found a video. Basically, all it is just storing values into some format and using that to just quickly access it. So in this case, we would use a dictionary. Um, so we pass in an empty dictionary at the start, and we just keep passing in memo as one of the parameters. And if we ever find the XY coordinates that we're currently at, we can mark those. Or if we find if we're back the XY coordinate that we've already calculated for, we can just get the value from there and just return that immediately. So we can avoid the, having to deal with this repeatedness. It makes it a lot more efficient. So the first time, my first solution failed with time limit issues, but the second one, this is the current one. Oops. This one, this one passed it even if it was very slow. I don't know if it will let me. No. Okay. This one's, I think it's O of N N and N N M M M N. But it has a lot of steps simply because of the number of steps in each iteration. So you're gonna have to check if this tuple is inside of the dictionary. You'll have to check if the current value is out of bounds. So that's like 2 checks, and then you'd also have to do another check where we had to check if we're at the target point, and that requires subtracting 1 from M. So that's another additional operation. So there's a lot of operations going on right here. This will be 1, 2, 4, basically like 5 here, 3 here. So it's 8. I don't know. I can't. I mean, it's O of 1, but whatever. Basically O of 1 here. So it's like 10 steps here minimum. And if all of those are false, then we have to go over here and then do 2 recursion calls and then add the values into the dictionary and then finally return the value from the dictionary at that point. So yeah, maybe I could have made it a little more efficient by doing this in case the dictionary goes or doesn't do constant time anymore for some reason. But yeah, this solution, I'm very happy with it. Was able to get it working. Learned memoization through the process of it. Learned or practiced how to use DFT and graphs. I have only done one problem like that, which was one problem with graphs and depth first traversal before. That was a what's it called? It was number of islands, I think that's what it was called. And yeah. So it was nice to get practice with that, learn how to use it, and do it on my own without help of others. Because the other one I did have help from other people. I had the concept right, but I hadn't done the recursive part right. So it's nice to be able to do it on my own with that. Put this into a visualizer, and the problem with this is, as you'll see right now, for a grid that's as small as 4x4, it has a lot of steps. Yeah, 216 steps for a 4x4, considering that M and N can go up to 100. This is not ideal. And I realized that when I saw this number. I thought that I had come up with a okay solution at least. Maybe not the best one, but definitely not the worst. Because I mean, the worst one I saw earlier. So I searched up like what am I missing? So yeah, I searched it up. Or well, originally I looked at the topics, combinatorics and math. Since there was two of these, I searched up what combinatorics was or whatever. It was basically just combination stuff. I had learned combination, but I wasn't really good at them. I'm okay at them, I think. I always mix them up with permutations. I had to get better at understanding these two things and separating them and understanding when to do one or when to do another and what type of problems to give you one or the other. I know Python has a built-in function, so I might have been able to just get away with using that, but yeah. So found out that that was a thing that we needed to do. Looked it up a couple of times. This is basically what we're doing. It's a combinatorics problem. As you can see, the n factorial over this number, factorial this number. So, yeah. Sorry. Yeah, and I looked over here. This is the memorization one, actually. Yeah. So this is a Fibonacci sequence one that they taught. It was almost immediate that I realized what the problem was. When she was originally explaining it, as you can see, the branch goes all the way down to Fib 1, from Fib 6, and Fib 1 is a base case. So, you know, we get this value from here, but we're essentially repeating substrings over and over again. So right here we have Fib 4. We're repeating that subtree over here. Repeating 3, 3, 3, repeating 2, 2, 2, 2, 2. So we're repeating a bunch, and that causes it to be 2, I think she said it was 2 of n, 2 to the power of n. So it's an exponential time complexity. But with memoization, it would drop down to O of n, because you'd basically eliminate all subtrees. Essentially all it does is it creates new base cases as you go along, which is cool. I thought that was cool. Look up combinatorials and combination stuff. I remember just reviewed basically discrete structures and all this stuff. It's pretty cool. But yeah. And then this, basically just use this to get to the final solution that I had, where we basically get the minimum number between the two axes that we can, or points that, what would it be? Basically the x-y coordinates, get the minimum of the two, and then we're going to make the total. This is the total number of possible moves that you can take for each path. So if we go 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. It's always 8. So we can guarantee that we have 8 moves. Or, well, not 8 moves, but basically m plus n minus 2 moves. I think this video also mentioned something about that. Yeah. Where you have m minus 1 moves and then n minus 2 moves to get to this point. And if you basically just simplify them, that's basically what you get, m plus n minus 2. So we got those two variables, we get the result. This is what we're going to use to find the factorial number. So it performed really well. And then we just iterate from in the range of the moves that we found earlier through the minimum number of moves right or downwards. We just find the factorial, or not the factorial, but the combination. Use the combinatorics principles and a little bit of math to move around some numbers to make it simpler. So this is all we had to do, is total minus I and I plus 1 with integer division between them, and result times all of that. And as we iterate through it, we'll basically do the factorial portions of this without having to do entire factorials of each one of them, which cuts down on the time a lot too. And at the end, we just return the result. So this is more of a math problem than it is really a graph problem or any of that. When I originally saw it, I thought, okay, this is a dynamic programming and graph problem. How do I do this? I have no knowledge, or very little knowledge, of both of them. My experience in graphs is very limited. I just learned them last month on my own from a textbook that briefly goes over basic graphs. Um, and I have done one leak code problem with them. So my experience is very limited with this type of stuff. Dynamic programming just always sounded scary. Um, and even the easy problems are a little weird for me. So I think the easy problem was like counting steps, leak code, or stairs, counting stairs. So I struggled with this one, and I think this one's a DP, right? Yeah. So like I've always struggled with the DP ones. It's like it's weird. I tried coin change. Uh, I got close, but the problem was that it had random numbers and they weren't sorted. So yeah, but it was cool. I think I like seeing being able to come up with a DFS or DFT graph solution using recursion, and then seeing how that kind of related to the combinatoric solution. I think um, I skipped to the end of this because I had already done the first one, and there was 5 approaches in this video. I'm assuming that there's more. What's the naive approach? What is this gonna say? Oh, is this gonna say what I think it's gonna say? It's gonna say my approach is naive. No, no, whatever. It's fine. But yeah, there's other problems. There's DP. Oh wait, so maybe I think the combinatorics might have just not been DP. I think that was just math. Uh, I think DP is close to what we have here. Um, but yeah, it's pretty cool seeing all the different solutions that you can come up with for that problem. I'm proud of what I was able to come up with, but I know it's not the greatest. And this one's better. That's all. That's how it always feels with leak code, bro. I always come up with a solution. It's not good, but it passes. Look at the real one. The real one just calls mine naive, and it's so sad. Anyways, that's all. Bye bye.